Hello everyone, welcome to this course on electrical circuit analysis. Today's topic is Thevenin's and Norton's theorem. These are the topics we are going to see today. First is the definition. Thevenin's theorem. Any two-terminal bilateral linear circuit can be replaced by an equivalent circuit consisting of a voltage source and a series impedances. Norton's theorem says that any two-terminal bilateral linear circuit can be replaced by an equivalent circuit consisting of a current source and a parallel impedances. Thevenin's and Norton theorem we can consider like a duality theorems, because we can convert from Thevenin's theorem to Norton's theorem as well as Norton's theorem to Thevenin's theorem. This is a simple conversion of voltage source to current source. So we can say that this theorem is a duality theorems. And the entire circuit in the left hand side can be replaced by a single voltage and impedance sources in case of Thevenin, and in case of Norton it can be replaced by a current source in parallel with the impedances. Okay, what is the need for these theorems? For example, consider that this is our electrical grid of our country India. Okay, so now in Bihar or in Patna there is some mela going on in Patna. For example, say Buddha Purnima mela is going on in Patna. Okay, now there will be an excess load on this Patna region, right? So if you want to study the effect of this excess load, what we can do, because we are not going to change the other loads or other sources on the other side, other part of the India. In that case, what we will be doing is we will be replacing the entire grid except the Patna into a equivalent circuit or equivalent networks with the help of the Thevenin or Norton. We will be using this entire, we will be converting the entire grid with a single source representing the sources at all other places and a single impedances, Thevenin's impedances representing the impedances of the other part of the network. By replacing entire network, we can study the effect of the increase in the load at the Patna. Okay. That is the need for this Thevenin equivalent circuit. We have to remove the circuit of our interest. We have to remove the circuit or the load impedance of our interest, and then we are looking to the circuit from that point. Okay, here if the in Patna we are going to apply some load, right? The Patna is our interest, right? So for that, what we have to do, we have to remove this Patna. From the Patna we are going to look into the other circuit of the network, right? So from Patna we have to look into what is the source, what is the impedance available in the network. Okay, for that, first thing is we have to do the Thevenin's Norton, Thevenin's impedance, right? For that, what we have to do, we have to make all other sources, dependent sources, we have to make it remain in the network. Only independent sources has to be removed, right? How you can remove the independent sources? By short circuiting the voltage source and open circuiting the current source, right? By that way you can remove the independent sources, right? Removing all the independent sources and making all the dependent sources on the circuit, we have to try to find out the impedances. Thevenin impedances. Once we have found out the Thevenin impedances, looking from this circuit or looking from this Patna, we have to look for the Thevenin voltage source or Norton voltage source, right? So for that, what you have to do, now you have to apply all the sources and impedances including the dependent and independent sources, and then we are trying to find out what is the voltage or what is the current across voltage across this Patna or voltage through this Patna grid, right? For we will be finding that, and we will be drawing the equivalent circuit. These are the steps which I have already described. First point, remove the impedance that is of interest. Here we have considered a Patna grid by open circuiting it in case of Thevenin's theorem and short circuiting it in case of Norton's theorem. Find Thevenin impedance as looked from the impedance of interest by removing all independent sources. And the third step is to find the Thevenin voltage as looked from the impedances of interest by inserting all independent sources. In case of Norton, we have to find the Norton current as looked from the impedance of interest by inserting all the dependent sources. The entire circuit except the impedance that of the interest is replaced by V Thevenin in series with Z Thevenin in case of a Thevenin equivalent circuit, and whereas in case of Norton theorem, IN is in parallel with Z Thevenin. Till now we have seen about the independent sources, right? With the dependent sources, what are the conditions we have to look into? There are some conditions which we have seen it earlier in case of superposition also. The same conditions apply here also. Okay. First thing is we should not remove the dependent sources. Okay. Whatever I've said in the superposition theorem, here also it applies. Like we should not remove the dependent sources. We can remove the independent sources, but dependent sources cannot be removed. Okay. And second thing is, while taking the duality, we have to be careful while converting from voltage source to current source or current source to voltage source. We have to take out the changes happening in the current or voltages while converting. Okay. And third point is the removal of impedance that is of interest should not affect the dependent sources. Okay. Suppose if you are going to remove some part of the network, if it is affecting the dependent sources, then we cannot remove it. Okay, we have to look for the other solutions. Okay, and here only one thing that is to be considered in excess to the superposition theorem is that this Z Thevenin we have to find in different way while considering the dependent sources. Okay. In case of independent sources alone, what we have done it, we have removed all the independent sources and then we try to find out Z Thevenin. Here Z Thevenin can be found out in two ways. First one is the way it was been described here. Z Thevenin is nothing but V Thevenin and divided by the Norton's current. Here in this dependent sources, we have to find out two circuits. Like one is with Thevenin voltage we have to find out, another one is Norton current also we have to find out, then only Z Thevenin can be calculated. Okay, whereas in case of independent sources we have removed all the sources and we have reduced the circuit using the parallel series combination of the impedances, and then we try to find out the Thevenin's impedances. Okay, here it is just opposite. Like after finding the V Thevenin and IN, we have to use those values to calculate the Z Thevenin. Okay, and this is one method. Okay, in case of another method, what we can do is we can instead of finding V Thevenin and IN, we can insert a new voltage across the point of interest. Okay. Across a point of interest, we can apply some not only voltage but we can apply some current source also. we have to consider as voltage or current source at the particular node of interest, and then we can calculate the Z Thevenin. This we can see it from the next slide. For example, we have taken one circuit with the one dependent source available in that particular network. Okay, this dependent source, it's a voltage source. Again, it is due to this diamond symbol, and the plus and minus, we can indicate that that is a voltage dependent source. This dependent source depends on the value of V0, where V0 is the voltage across this 5 plus 0 j ohms. Okay, so because this value of this voltage depends on some value, we are calling it as a dependent source. Okay, so now we try to find out the Thevenin voltage, Thevenin Norton's current, and the Thevenin impedance also from the for the circuit. Okay, for that first we have to remove the part which is of our interest. Okay, so let us consider that this much amount of load we are going to add it in the Patna grid. So what we can do is we can remove this terminal, and then we are looking into, from this terminal we are looking into the circuit and try to find out what is the Thevenin voltage and Thevenin current, Thevenin voltage and Thevenin impedance, and Norton current and Thevenin impedance also. Okay, for that first we have to remove this. We have to open circuit this in case of Thevenin's voltage, and we have to short circuit in case of this Norton's current. While finding the Norton's current, we have to short circuit it. Okay. In the next slides, we are going to see about how this can be found out. Okay. Here we are trying to find out the Thevenin's voltage. Okay. So we are open circuiting the point of interest, like open circuiting the particular node, and we are trying to find it out. Okay, here I have used the mesh equations. Okay, we can use the nodal voltage equations also, but here I have used the mesh equations. But it is a task for you. You can try with the nodal voltage equation also, and try to find out whether you are getting the same VThevenin or not. Okay, so here I have considered, for finding the Thevenin voltage, what we have to do, we have to have all the independent sources as well as dependent sources in the circuit, and we have to try to find out what is the voltage across the point of interest. Okay, so for that we are just removing this, and we are trying to find out the voltage on this particular circuit across this node. Okay, so first we have considered, since there are two loops, we can have a two loop current I1 and I2. Okay, this is not the branch current. Okay, what is the branch current here? Branch current of this particular resistor, it is I1 minus I2. Okay, here it is simply I1. I1 represents the loop current. It is not the branch current. Okay, so we have two loops, 1 and 2. So the impedance will be having 2 into 2 matrix. Okay, this is for first loop and this is for second loop, and this is for first loop and this is for second loop. Okay, so while considering the first loop, okay, I1, what we can see, what are the impedances it is coming across, this 5 plus 0 j and this 2.2353 plus 1.6541 j. So we have to add these two resistances or impedances, and then we have to represent. Okay, 5 plus 2.2353, it is 7.2353 plus what, plus the imaginary part. Okay, so when this current, this 1, right, this is 1, it includes this loop current. Okay, loop current I1. Next it is 1 and 2. Okay, now we will try to find out the Norton current. Okay, for doing the Norton current, or finding the Norton current, what we have to do, we have to short circuit the desired terminal, right? We have to short circuit the desired terminal, and we have to try to find out what is the current flowing through this particular short circuited desired terminal, right? Okay. So here also we can see that there are three loops are there. So we have considered I1, I2 and I3 as three loops. Right? Here also we are trying to write the mesh equation. Right? Here we are trying to write the mesh equation, but we can use the nodal voltages also to find the IN. Okay, that you can try to do it and try to check whether you are getting the same IN as here. Okay, so here also we have considered three loops. So we are having a 3 into 3 impedance matrices. Okay, so this is for first loop, and this is for second loop, and this is for third loop. And here also this is for first loop, and this is for second loop, and this is for third. Okay, so when you are considering a first loop, what are the impedances it is coming across? Again the same thing. This impedances and this impedances are coming in like it is in relation with the I1, so these can be added up and it can be represented in the diagonal elements. Okay, so first loop in relation with the second loop, right? First loop relating the second loop, right? What is the element present in the first loop relating with the second loop? So this is the element, so it is a negative of that, because while considering the first loop, we are considering that first loop current as a positive current. The direction of the, whatever the direction of that first loop will be considered as a positive. The other things will be considered as a negative. Okay, so since the direction of this one is in this way, so the loop current direction will be considered as positive, and the branch current also, it is considered as branch current also flows in this way. Okay, and what about this first loop and third loop? There is no relation, right? There is no impedance connecting this first loop and third loop, so it is 0, 0. Okay, and now considering a second loop. Okay, considering a second loop, what is the impedance available in this I2? Only this impedance is available. Okay, but before that we have to find out, try to find out what is the impedances relating both I2 and I1. Here we are considering I2 loop, so the loop current direction of the loop of the direction of this loop is considered as a positive. Okay, so now this is considered as positive and this is considered as negative. Okay, so this is now in this case what we have to do, this is considered as positive and this is considered as negative. Sorry. This is considered as negative. Okay, so that's why it is negative of that particular resistances. Okay, so next one is like this is second loop and second. Okay, so only second loop is considered. So whatever the resistance coming across this second loop, we have to take it as a positive value. Okay, and similarly the second loop and third loop. Okay, what is the if you can see that there is no other impedances coming across this I2 and I3, so we are putting at 0, 0. Okay, it is negative of that, but since it is 0, we are mentioning 0, 0. Okay, similarly, since I have already told you this is a symmetrical matrix, we are including only the independent sources. So what we can do is simply we can copy that of diagonal elements. This minus 2i3 2.2353, it will be coming over here, and 0, 0 will be coming here, and this 0, 0 will be coming here. Okay, and only the diagonal elements we need to determine. Okay, and what about the 3, 3, third loop? What are the impedances coming across this third loop? Only this resistance 1 plus 0 ohms is coming across, J0 ohms is coming across this third loop, right? So we are including that also. Okay, so this impedances what we will call? We will call it as a mesh impedances. Okay, because we are trying to find out the impedance due to the mesh equation. Okay, so that's why we are calling as a mesh impedances. Mesh impedance into the mesh current. What is that mesh current or loop current? I1, I2, I3. right? I1, I2, I3 equal to the voltage rise in the particular loops. Okay, first loop, this is for first loop, and this is for second loop, and this is for third loop. Third loop. Right, for the first loop only one voltage source is there, that is 10 plus 0 j, and this voltage source, it is aligned along with the I1, because the positive terminal, it is aligning with the current direction of I1. That's why we are considering as a positive value. Okay, and similarly, when we are considering this I2, whatever the voltage source is coming across this I2 loop, we have to consider there is no other voltage source along with this loop except this dependent source is 0.5 V0, right? So the current through this this will be like this, right? Current through the dependent sources, current through this dependent sources, that is I2, will be in this direction, which is aligned opposite to that of 0.5 V0. So we are considering as minus 0.5 V0. Okay, and while considering the loop 3, when considering the loop 3, the current direction of the loop current is this way, right? Current direction of this loop current is in this way. It is aligned with the dependent voltage source, so we are considering as a positive value. Okay, here we have to note down that previously there is only one V0 was coming across this one. Because of this third loop, we are having the another voltage also, like a dependent element also included in this equation, right? So as I have already told, we have to write the equation for the dependent source also. Okay, so dependent source V0 is equal to, what is V0? V0 is nothing but your voltage drop across this 5 plus 0 ohm as said earlier. Okay, after substituting this V0 in this matrix equation, here since we have two V0, there will be two changes in the impedance matrix. As said before, the same value is coming here, and here one more additional term is coming here, it is minus 2.5. Okay, see, since V0 depends on I1, only the I1 elements will be changing. Okay, what is this one? This is for I1, right? This is for I1, I2 and I3. So the I1 value alone changes. Okay, I1 value alone changes. Okay. So here also we can see the equation for the independent sources are symmetrical, rest for the equation for the dependent sources are unsymmetrical. Here also we are trying to find out I1, I2, I3, and what is I3? IN, what is IN? It is similar to I3, right? Both are aligned. There is no other impedances or no other circuit in between. So I3 is equal to IN. Okay, so here we are trying to find out IN and I3. This is also 3. This is 3.333 plus 0j amps. Now we are trying to find out the Z Thevenin. Z Thevenin can be find out in two ways, as I said already. Z Thevenin, first one is like Z Thevenin can be find using this V Thevenin, Thevenin voltage, as well as IN, Norton current. Thevenin voltage and Norton current we have already found out. From those values we can calculate the Z Thevenin. Another method is we can apply an external voltage at the desired node and making all other independent sources removed from the network. Okay, so we are removing the independent sources and we are applying some desired known voltages at the desired node. Okay, after that we are trying to find out what is Z Thevenin. Now we are trying to find out the Z Thevenin. Z Thevenin can be found out in two ways. One is using the V Thevenin, that is the Thevenin voltage, and another one is the Norton current, that is IN. Okay, from this we can find out the Z Thevenin. Another method is we can apply some known voltage at the desired node and try to find out the current in that branch. From that we can calculate Z Thevenin. For that, what we have to do, we have to remove all the independent sources. We have, as said earlier, the dependent sources will remain in the circuit. Okay, here the independent sources, this voltage source. So how it can be removed? It can be removed by short circuiting the voltage source. Okay, now I am applying some known voltage of 1 at an angle 0 at the desired terminal of this one. Okay, and I am trying to find out what is the current through this terminal. Okay. Now similarly, as said earlier, similarly we can try to find out what is the loop currents in these circuit, and then we can find out what is I3 at this point. Okay, flowing through this particular branch. I think so, here also, like what is the changes we can observe? There is no independent sources, so the independent sources are made to 0. Okay, so initially it was 10 plus 0j, now it is 0 plus 0j. Okay, and apart from that, there is an additional term like minus V1. Why it is minus V1? The current direction is in this way. That is, the current is flowing into this plus, right, plus of the voltage source. So that's why we are having the minus. Okay, V1 is nothing but the known voltage. Here it is 1 at an angle 0. Okay, after applying everything, like this is the due to this independent sources, and this is due to the dependent sources. Like we have applied the dependent equations, substituting the dependent equation in this one, we got this one. Okay, from this we can calculate what is I1, I2, I3. Okay, now this is the voltage at this branch, and I3 is the current through that branch, and if you are calculating, then we can get the Z Thevenin. It is considered as minus, as I told already, the current is going inside this voltage source. That's why it is minus. Okay, when we are applying V1 by I3, we got this 1 plus 0j, which is similar to this earlier version also. Thus, in two ways we can find the Z Thevenin. Okay. Regarding the duality, the same slide only, whatever I have used in the superposition theorem, here also used, because to make you understand the importance of the duality, like duality, like the steps we have to take in care while applying the duality, I have included it here. Okay, similarly whatever I have said earlier, the same thing here also, like I0, V0, that is the external current and voltages, that is current going out of this node, this circuit, and V0 is the voltage across this circuit, remains the same, whereas the current through this voltage source and current obtained by after converting the voltage source, it is different. Okay, and whereas the current through this Z and current through this Z will be different. Okay, okay, so this should not be IZ. Okay, so this will not be IZ, current will be different. How the current will be? It is IZ is equal to I minus I0, whereas here IZ is equal to I0. VZ is nothing but V minus V0 here, VZ is equal to V0 here. Okay, so IZ, VZ, it is different. Okay, similarly the current IS is nothing but the voltage source currents. Okay, the voltage the current from the source. Okay, so IS is nothing but here I0, but here IS is nothing but I0 plus IZ. Okay, so Vs is the voltage across the source. Okay, voltage across the source, it is V0, it is not V. Okay, it is the current from the voltage source, this is the voltage across the current source, those are different. Okay, okay. this slide also we have discussed in superposition theorem, but here another thing is, earlier in that one we have seen that removal of any independent sources may affect the dependent sources, then we cannot use that circuit, right? Here it is like removal of that particular impedance of interest. What is the impedance of interest? From through which we are going to look into, from through which we are trying to make it as an equivalent circuit. Okay, once we are removing this impedances, then because of removal, that I naught becomes 0, right? I naught becomes 0, the dependent sources becomes 0. Okay, so this is not allowed. Okay, so we cannot calculate using this circuit. Here also similarly, if you are short circuiting the desired terminals, then V naught will be 0. We cannot use this dependent source. Actually, this should be this is the current source, not the voltage source, right? This should be a current source. This current source will not appear because I naught is 0, so this current dependent source will not appear. Here the voltage will be 0, so the voltage dependent source will be 0 here. So in that case, we cannot apply the Thevenin's theorem. But how we can do it is, we can, instead of this, you are taking this as an equivalent circuit, what we can do it, we can cut short this. Now the equivalent circuit you can try to find out only up to this. Okay, here also we can try to find out the equivalent circuit only up to this point. Okay, this point it can be included in this equation. Okay, this point we can include it here. Okay, so this point is included it here. Okay, and then we can try to find out the Z Thevenin and V Thevenin and IN. Okay. So if there is a dependent sources which depends on the current or voltage or the impedance value of the impedance of our interest, then we cannot do the Thevenin as such, Thevenin or Norton's as such. What we have to do, we have to include that dependent sources to the desired impedances. Okay, then we can find out the V Thevenin and I Thevenin. Okay. Okay, for self-assessment, two problems are given, one with the only independent sources, another with the dependent sources. You can try to find out what is the V Thevenin as well as Norton current, Norton current through this terminal 3 plus 3 J3 ohms, and try to verify the Thevenin and Norton's theorem. Okay, it can be given as a self-assessment and you can do it and submit it. Thank you.